This is an example of a hypothesis test for two averages. I'm comparing two battery lives for Energix and Durabell's battery. Suppose I sampled 101 of each. The E brand lasts for 10 hours on average with a standard deviation of 2. D brand lasts for 9.5 with a standard deviation of 2.5. And I'm testing for a difference. Null hypothesis when I'm comparing two groups is always going to be that they are equal to one another. This is the same thing as claiming that there is no difference in the two groups. So when I have my model, the center is going to be 0, representing that claim of no difference. Alternative hypothesis, I can either have more, less, or not the same. In this problem, I'm not given a single direction, more or less. I'm testing for a difference, so I'm going to have a two-tailed test. Degree of freedom. This is a bit of a lie. This is a rough estimate for what the degree of freedom is. I will show you what it actually is in a calculator at the end of this process to show you how close things are. My end results will be reasonably similar, even if my degree of freedom is slightly different at the start here. And my degree of freedom is going to be the smaller of the two degree of freedoms. Both my groups had 101, so my degrees of freedom are 100 and 100, so I'm going to be using a rough estimate, a degree of freedom of 100 or so. And my standard deviation is first standard deviation squared, so that's 2 squared over number of samples, 101, and second standard deviation squared, 2.5 squared over number of samples. This model is pretty forgiving in that if I get the order off on which thing is my first group or the second group, I've got addition, so it won't really matter that much. If I type this into my calculator, I get the square root of 2 squared divided by 101 plus 2.5 squared over 101 gives me a standard deviation of 0.319 or so. My p-value, this is the likelihood of my sample data, and I'm doing E minus D. I made this choice. I could have easily done the other way. It would be okay, but I just have to be consistent. So E brand had an average of 10. D brand had an average of 9.5. I'm testing for a difference, so I'm going to have a two-tailed test here. So I'm testing to see if it's different than 0.5. Units for this whole problem are hours. So when I draw my curve, I got 0 in the center. I'm counting by 0.319. And the value that I detected for a difference was 0.5. This is a two-tailed test, so I'm going to shade in both directions. And whatever t-score this is in the positive direction, this is going to be the same t-score in the negative direction. So if this is like 1.2, this is going to be negative 1.2. So let's find those t-scores or those test statistics and then look them up. So t is equal to my value. Well, my value is my difference, 0.5. So I'm going to take my data difference minus the center. The center is the claim, that's 0. And I'm dividing this by the standard deviation. My standard deviation for this model was at 0.319 number. So I have 0.5 divided by 0.319. This gives me a t-score on this upper side of 1.567, and my t-score on this other side is negative 1.5674. When I'm looking up t-scores, I use TCDF. So my p-value in this case is going to be 2 times either the right side, if you want to look up the area of the right side, or 2 times the left side if you want to look up the size of the left tail. I'm doing this multiplication by 2 here because I'm testing for a difference. If this was strictly a greater test, it would just be right. If this was strictly a less test, it would just be that left value. I'm going to set this up for the right tail. So for the right side, TCDF, I'm going to have my low t-score for the part that's shaded in, comma the high t-score. Well, there is no high. It just keeps going on forever, right? And then finally, my degree of freedom. So I'm going to have 2 CDF. My low t-score, this is my value. That's not my t-score. My t-score is what I got when I typed this into a calculator. So if it helps, you might even want to write your t-scores next to your values on your curve so you don't forget what you're working with. So this started low value of 1.5674, comma, and it continued forever on this right side towards infinity. So for a high value, I'm going to type in infinity if my calculator has it, or I'm just going to go to town on that 9 button and just get a really, really large t-score that effectively acts the same as infinity. My degree of freedom for this, I am estimating it to be 100. That's just a rough estimate. We'll see what it actually is here in a second. To do this inside of my calculator, I am either going into second vars if I am in a TI-83 or an 89, 83 or 84. I'm going to go into stat list if I'm in a TI-89, and I'm going to choose the option for F5 for distribution. And if I'm using GeoGebra, I'm going to open it up and go into probability. And I'm going to choose the option for the student t distribution. Let's do it on each just to see what we're working with. TI-89. I'm going into stat list editor, so apps, stat list editor. Distribution is up there at F5, so F5. I'm choosing TCDF from 1.5674 for the low value up to infinity. I can do, my infinity is the green infinity button right there. My degree of freedom, I'm saying, is about 100. It's actually larger. I'm assuming I have less control than I really do. That's fine. When I do this, I end up getting a CDF of 0.06 or so. So if I do 2 times that value, I'm ending up with a p-value of about 12% or so. Let me show you the same thing now in my TI-84. So I'm doing 2 times second vars. I'm choosing the option for TCDF from 1.5674 up to infinity. My degree of freedom is 100. I see that 12% again. The nice thing about the TI-83 and 84 is I can actually do the math where I have like the 2 times all in one step. Where when I did this thing with the TI-89, it just gave me the 6% for one tail, and I still had to multiply that by 2. Not that hard to multiply it by 2, but I'm still a lazy person, so I welcome anything to do less work. Thank you, TI-83 and 84. I'll show you how to do this in GeoGebra in a second as well, but let's just talk about conclusion before I leave the page here. If your p-value is low, the null must go. At a 5% alpha level, though, I would not say 12% is low. I would say that's high. If my p-value is large, I would fail to reject the null hypothesis, which means I have no evidence in a different average battery life. So if I wanted to make a commercial and say that Durabells outlast Energex, I legally couldn't do that. I don't have the evidence to do so. Let me show you the same thing now inside of GeoGebra. So I'm opening up GeoGebra. I'm going into probability. Where it says normal, I'm choosing the option for student distribution. And my degree of freedom, 100. I'm going to make this thing shaded to the left. I could take either tail. Negative 1.5674. So if I was looking at the left side, this would give me 6%. I could have done the right side. Let me show you the right side. So I'm going to click this button to shade it to the right. My t-score on the right side was a positive. That's giving me exactly that same value of 6% for both the left tail and the right tail. 6% plus 6% is giving me that 12%. That's why I'm multiplying it by 2. So in GeoGebra, I'm choosing probability, I'm choosing the student distribution, and then I'm choosing which tail I want to look up, the left or the right, and just base that off of what your picture is. Okay, I wanted to verify with you what this sort of looked like if I actually did the whole thing using technology instead. So I'm going to do a t difference of means test just to kind of show you how that degree of freedom would actually change. My first average was 10. The standard deviation there was 2 for 101 samples. My other average is 9.5 with a standard deviation of 2.5 for 101 samples. I'm still ending up with a p-value of 12% or so, so I'm getting effectively the same p-value. The actual degree of freedom I was calling 100 was considerably larger at 191. The formula for coming up with the degree of freedom is really, really messy though. So this method that I'm doing by just taking the smaller will give you a pretty reasonable estimate. But do keep that in mind that when you're typing this stuff into your calculator and you're getting this p-value of 12%, that is an estimate. The actual value is 11.8%, okay? Doesn't change my final conclusion though, so assuming that this isn't a close thing, it's not going to affect your end results all that much. All the same, something to be aware of.